All right there, Chem Scholars. We're going to get into KSP today. It's really KEQ still. It's just limited to one specific type of reaction. Okay, we'll get into that now. All right, so the SP stands for solubility product. Okay, so we're talking about solubility. We're just talking about dissolving things. Notice a reaction down here. I'll go through some of the explanations, but all that we're doing is taking a solid, putting it in water, and looking at its solubility, okay? That's all it really is. In order to talk about a reaction for equilibrium, right, we have to have a reversible process. So this is only true when we're talking about a saturated solution, okay? So I highlighted that in yellow here so you understand. KSP is only for dissociation reactions where we're talking about a saturated solution. That's it. If I asked you to write out your KEQ expression for this reaction, we do products over reactants, but the reactant's a solid, so it's over 1. So it's just potassium squared times sulfate. That's it. Okay? So it's called solubility product because we're looking at the products. Okay, and from a math point of view, we're multiplying. The answer of multiplication is a product, so it's a solubility product. Okay, so if I say KSP or I say the solubility product, okay, we're talking about KSP. It's just equilibrium for dissociation reactions. So really, we're not doing anything new today, just focusing in on that type of reaction. All right. So let's say we have a situation where we're told that 1.2 moles of potassium sulfate will dissolve in a liter of water to make a saturated solution. Okay, so 1.2 moles in a liter is 1.2 molar. Okay, so I'm putting it in molars. Now, when we talk about an ice table, we usually, begin with I, the initials. Well, this is a solid. We don't care what its initial is. The products are starting at 0. But here's the key. I told you that the maximum amount of potassium sulfate that would dissolve was 1.2 molar. That's its change. Now, again, it's a solid. It doesn't matter, right? No, but it's setting up the stoichiometry. What is the ratio between potassium sulfate and potassium? Well, it's a 2-to-1 ratio. So that means that I know that if this is dissolving by 1.2 molar, then I'm getting 2.4 molar concentration of potassium ions, and I'm getting 1.2 molar concentration of sulfate ions increasing. And so at equilibrium, this is 2.4 molar, this is 1.2, and we're back to the fact that the solid doesn't matter. Oops, lost my thing there. All right. So that's it. There's nothing fancy, and it's going to be simple ratios and everything. So it's really a pretty simple process. Okay. So once we fill out the ice table, then if I wanted to actually calculate out KSP, well, we said KSP was concentration potassium squared times concentration of sulfate. So I take 2.4 squared times 1.2, and that tells me that KSP for potassium sulfate is 6.9. Notice that the value of KSP, or KEQ if you want to call it that, is greater than 1. We said earlier that when it's greater than 1, it means products are favored. Well, we're talking about a solubility reaction or dissociation. If it's something that's soluble, right, we know our solubility rules, it should have a value greater than 1. That's why it's soluble. Okay, so that whole solubility rules and everything else really comes from KSP. We could have done this back then, but it makes more sense to me to do it now. Okay, so if the solubility of chromium 3 chloride is 7.87 molars, what is the value of KSP for chromium 3 chloride? All right, take a minute, give it a try, pause the video, because I'm going to go on. All right, so we set up our ice table. The solid really doesn't matter. These two, the product started at 0. Now we were told, oh, sorry, people. I don't know why it keeps switching for me. We know that the solubility we're told was 7.87 molar, so that's how much we're using of the chromium chloride. Doesn't matter how much we start with, doesn't matter how much we end with. We're just trying to figure out how much we use because that's going to tell us how much chromium we're going to get and how much chloride we're going to make. And so at equilibrium, we know the chromium is 7.87, and we know that the chloride is 23.61 molar. And now I set up my expression. Oh, sorry. We're doing KSP is concentration of chromium times concentration of chloride cubed. Now I just substitute in the 7.87 for the chromium, the 23.61 for the chloride, and I get 1.04 times 10 to the fifth. Okay, really nothing new to this. Okay, but let's look at it from the reverse point of view. So what if I give you KSP and I ask you for the solubility? Well, we did some problems kind of like this the other day where we used X's for the concentrations and we worked backwards. Okay, so that's really all that this is going to be. Keep in mind that when we talk, let's say that, so KSP for potassium sulfate is 2 times 10 to the negative 29th. Okay, so I'm giving you the value of KSP right here. Okay, so I set up my reaction and I know it has to be a dissociation reaction. So I take calcium phosphate, I break it down into 3 calcium ions, 2 phosphate ions. We've written out dissociation reactions before, that's not new. And we want to find the solubility. So really I'm trying to find X here. Well, by stoichiometry, that means that this change has to be plus 3x and this change has to be plus 2x. And so at equilibrium, this is going to be 3x, this is going to be 2x. And now I set up my equilibrium expression, KSP, or KEQ if you want to call it. It's products over reactants. The reactant's always going to be a solid in the KSP process, and I do mean always. Okay, so we're talking about calcium cubed times phosphate squared. I substitute in now, we were given KSP is 2 times 10 to the negative 29th. We figured out that calcium is 3x. And the potassium is 2x. Now I just got to do a little math. 3x quantity cubed is 27x cubed. 2x quantity squared is 4x squared. 27x cubed times 4x squared is 108x to the fifth. So I'm going to divide by 108, and then I'm going to take the fifth root. Okay. If you want to do fifth root, there's a couple ways you can do it on your calculator. One of them is by hitting the math button. Okay, and you'll see that the, let me see if I can get it on the screen better. Maybe you can see it now. Okay, so math, option 5, okay, you see it lets you take any root that you want. Or what I could do is, let me actually shift my camera around and I'll show it to you a different way. Give me 1 second here. Oh, it's not using that camera. Oh, that stinks. Okay, I thought it was using my dock camera, but it's not. Oh, I could do it this way still. Okay, see, we work things out. All right, so let me flip it around. Flipperooski. All right, so let's say I wanted to take the fifth root of a number. So I want to take the fifth root of 128. I could do either hit fifth root and go, so I do 5 and I hit the math button. I don't want second, I want math. 5. Okay, so I told it fifth root by hitting that 5 in advance, and now I do 128 and it tells me, all right, it's 2.64. Okay, great. Now another way I could do it is I do 128 and I hit the little caret symbol and I say do it to the 1/5. So I could do 1 divided by 5 and it gives me the same answer. What do you know? Okay, so the fifth root means 1/5 or whatever else. Okay, anyway, there's 2 ways that you could go about doing that stuff there. All right, so try this one. If KSP for silver carbonate is 8.1 times 10 to the negative 12, what is its solubility? All right, so pause the video, give it a try, but I'm going to explain it now. So first thing I'm going to do is set up my reaction, silver carbonate, Ag2CO3. So I'm going to get 2 silver ions, 1 carbonate ion. Okay, I know that the first line is always going to be the same thing. The solid we don't care about. These are going to start at 0. The solubility is going to be negative x. That means this is going up by 2x. I keep doing that. I don't even know how I'm doing it. That's going to be x. So we're going to end up at 2x and x. So really, the ice table is almost not needed in this case. And I'm not really going to be that upset if you don't have it, although from a partial credit point of view, if you made a mistake and you don't have the ice table, you would lose points. Okay. So notice what happens here. Whatever the coefficient is going to appear twice. I get it here, I get it here. Okay? Carbonate had a coefficient of 1, so this is a 1, and up here would be a 1 for the exponent. So now I just have to square 2x, I get 4x squared times x, that gives me 4x cubed. I divide by 4, I take the cube root, I got 1.27 times 10 to the negative fourth molars. Remember, it's got to be in molars. That's, I guess, another common little mistake that people make. Okay? So that's it. There's really nothing new to this. Okay? So my advice is to try one or two of the questions in the practice packet about it. Okay? So we'll do an example or two in class tomorrow? No. Yeah, tomorrow, Friday. Yeah, that'll work. Okay. So that's it. All right. Hopefully this makes sense to you. I'm going to ask you to try and answer one or two follow-up questions. Okay, so there is something else you have to do with this. But that's it for today. All right. So if you have questions, send me a message, an email, whatever else. I will be out for the funeral until the afternoon, but I will be back after that. Bye.